Alright, so our topic for today is circular motion. Angular displacement is for an object moving in a circle from A to B. The angular displacement is theta. For a small value of theta, the angular displacement is a vector quantity. The distance covered from A to B is given by S, which is your arc length, equals to R, which is your radius, multiplied by theta, which is your angular displacement. और पूरे सर्कल के लिए जो circumference होती है वो होती है 2 pi r. 3 यूनिट जनरली यूज़ किए जाते हैं एंगुलर डिस्प्लेसमेंट को डिस्क्राइब करने के लिए. एक होता है डिग्रीज, दूसरा होता है रेवोल्यूशंस और तीसरा उसका SI यूनिट होता है जो कि रेडियंस है. एक 1 radian is defined as the angle subtended from the center of a circle which intercepts an arc equal in length to the radius of the circle. 1 revolution equals to 2 pi rad, which is also equal to 360 degrees. 1 radian equals to 360 over 2 pi, which is also equal to 57.3 degrees. Angular velocity is the rate of change of angular displacement. उसका SI unit rads per second होता है. For an object moving in a circle from A to B, उसकी angular velocity इस तरह दी जाती है: change in angular displacement over change in time. जहाँ पे time वो t वो time taken है A से B तक जाने के लिए. इसका जो angular acceleration है इसका definition है your rate of change of angular velocity. उसका formula है angular acceleration equals to change in angular velocity over change in time. और इसका SI यूनिट होता है rads per second square. Angular velocity is a vector quantity क्योंकि उसमें हमेशा magnitude और direction होता है, and its direction is always along the axis of rotation. Time period of revolution is the time taken for the object to complete one rotation, and it's given by t equals to 2 pi over angular velocity. This is derived from the formula of angular velocity by simply substituting theta over theta with 2 over pi, because the object covers a full circle and there are 2 pi radians in one complete rotation. Frequency. The number of revolutions covered per second is called the frequency of rotation. Hence, frequency equals to number of revolutions over time, which is also equal to 1 over t, where t is the time period measured in seconds. अगर हम substitute करें f equals to 1 over t in t equals to 2 pi over your angular velocity, this gives us your angular velocity is equal to 2 pi multiplied by f. This is your relation between linear and angular quantities: angular displacement, velocity and acceleration. So displacement equals to r, which is your radius, multiplied by theta, which is your angular displacement. Velocity is equal to your r radius multiplied by your angular velocity, and acceleration is equal to your radius multiplied by your angular acceleration. Centripetal acceleration. If an object is moving in a circle at a constant radius with constant speed, its direction is constantly changing, hence velocity is not constant. So although the speed is constant, उसकी direction जो velocity की है वो हर वक्त change होती रहती है और हमेशा circle के tangent पे होती है. तो अगर एक object constant speed से move कर रहा है तो it's always accelerating क्योंकि उसकी velocity basically हमेशा change होती रहती है. At every point in its motion, a particle moving in a circle has a change in velocity due to a change in direction. This change in velocity due to changing direction is called centripetal acceleration and is given by multiplying your angular velocity by your standard velocity, linear velocity, you may say that. But velocity equals to r, which is your radius, multiplied by your angular velocity. Hence, acceleration equals to r, which is your radius, multiplied by your angular velocity squared. Hence, this is also equal to v squared over r. Angular acceleration: when an object rotates about an axis located in it, the object is said to have a rotational motion. If the angular velocity of a body in rotational motion changes, the body has an angular acceleration. Hence, angular acceleration is defined as the rate of change of angular velocity. Angular acceleration A equals to d multiplied by your angular velocity over d multiplied by your time period. The relation between angular acceleration and linear acceleration can be found by simply differentiating v equals to r multiplied by your angular velocity with respect to t on both sides. Hence, you can refer to this formula: acceleration equals to r, which is your radius, multiplied by your angular acceleration. You can refer to these formulas for better comprehension. Centripetal force: as the object is moving in a circle, there must be a force जो कि उसको रोक रही है अपने सर्कुलर पाथ से निकलने से। इस फोर्स को सेंट्रीपिटल फोर्स कहते हैं और इसका फॉर्मूला इस तरह दिया जाता है. Centripetal force is equal to your mass multiplied by your acceleration. Hence, F is equal to m, which is your mass multiplied by your velocity multiplied by your angular velocity. So mass multiplied by your radius multiplied by your angular velocity squared. Hence, mass multiplied by your velocity squared over your radius. The direction of the centripetal force is always towards the center of the circle. And if there is no centripetal force, or if the centripetal force मतलब अचानक से गायब हो जाती है, जो ऑब्जेक्ट है वो सर्कल के टेंजेंट के मुताबिक फ्लाई हो जाएगा. मोमेंट ऑफ इनर्शिया, आपको एक क्वांटिटी अंडरस्टैंड करनी चाहिए जो कि ऑब्जेक्ट की रोटेशन के मुताबिक है. You should also know the concept of torque produced when objects move in a circular motion and relate torque to moment of inertia. You should also know the formula for the moment of inertia for various objects like rods, or disc and spheres. ये formulas नीचे summarize हुए हुए हैं. You can refer to these for better comprehension. Angular momentum. Translation motion में angular momentum describes the motion of particles जो कि rotational motion में होते हैं. हालांकि angular momentum describes their motion. Then angular momentum of a particle is simply its linear momentum multiplied by its distance from the axis of rotation. Hence, L equals to mass multiplied by velocity multiplied by your radius. But velocity equals to your radius multiplied by your angular velocity. Hence, L is equal to mass multiplied by your radius squared multiplied by your angular velocity. The principle of conservation of angular momentum states that the total angular momentum of a system is constant unless an external torque acts on it. L is equal to mr squared multiplied by your angular velocity, and this is constant. Motion in a vertical circle. For an object tied to a string being rotated in a circle vertically, the weight of the object needs to be considered and the forces acting on the object need to be resolved in such a way that the resultant of these forces is equal to the centripetal force. For an object at the top of the circle, weight and tension both act in the downwards direction with the center of the circle. The resultant is the centripetal force. For an object at the bottom of the circle, the weight acts in the downwards direction while the tension acts in the upwards direction. Hence, it's the same thing, but here you add your mg and here you subtract mg. It may be conjectured from this equation that the tension in the spring when the object is at the bottom is greater than the weight of the object. This is because the resultant centripetal force must act in the upwards direction towards the center of the circle for the object to keep moving in the circle. So d top equals to d bottom is less than d bottom. Hence, if an object is tied to a string and rotated in the vertical circle, the string is likely to break due to higher tension when the object is at the bottom than at the top. In other positions, the components of weight must be solved and resultant should be calculated with the tension to find the centripetal force acting on the object. Motion in a horizontal circle. If an object is tied to a string and rotated in a circle horizontally using the string, the centripetal force would just be the tension in the string because there is no force of gravity acting on it. So F is equal to D, which is also equal to mv square over r. Here are other key areas you should be aware of, which include your rotational kinetic energy, your artificial satellites, your real and apparent weights, your orbital velocity, and all of the relevant formulas must. Alright, so our topic for today is motion and forces. Kinematics is the study of an object's motion in terms of displacement, velocity, and acceleration. Displacement is the shortest linear distance traveled by an object from one point to another. It's a vector quantity as it has magnitude and direction. उसका ऐसा unit meter होता है. Velocity है rate of change of displacement. इसका ऐसा unit meters per second है. और ये एक vector quantity है जो कि इसका direction और magnitude होता है. Velocity का formula है change in displacement over change in time. Acceleration is the rate of change of velocity. इसका ऐसा unit होता है meters per second square. ये एक vector quantity है as it has magnitude and direction. The formula for acceleration is velocity, change in velocity over change in time. So there are two types of vertical motion in one dimension. One is without air resistance and one is with air resistance. Without a resistance, the only force acting on the falling object is the gravitational pull या फिर उसका weight. Acceleration की value है वो -9.81 meters per second square होती है, डेटा बुकलेट में दी होती है. With a resistance, जो जब ऑब्जेक्ट रिलीज होते हैं इनिशियली, उसकी velocity जो है वो 0 होती है. At the moment of release, the only force acting on the object is the weight of the object. The force due to a resistance is negligible. जैसे ऑब्जेक्ट फॉल होता है उसकी रेजिस्टेंस ऊपर की तरफ इंक्रीज होती है जबकि वेट उसका कांस्टेंट रहता है, जिसकी वजह से रिजल्टेंट फोर्स वो कम होती रहती है. जैसे कि रिजल्टेंट फोर्स कम होती है, द एक्सेलरेशन ऑफ द ऑब्जेक्ट आल्सो डिक्रीजेस, उसकी एक्सेलरेशन भी कम होती रहती है. यू कैन रेफर टू द सेकंड लॉ ऑफ न्यूटन. सिंस एक्सेलरेशन एंड वेलोसिटी सेम डायरेक्शन में होते हैं, वेलोसिटी भी बढ़ती रहती है. थोड़ी देर के बाद रेजिस्टेंस और वेट इक्वल हो जाते हैं, जिसकी वजह से रिजल्टेंट फोर्स भी ज़ीरो हो जाता है और उसकी वजह से एक्सेलरेशन भी ज़ीरो होती है. आप इन डायग्राम्स को पढ़ सकते हैं फॉर कॉम्प्रिहेंशन. जब भी रिजल्टेंट फोर्स ज़ीरो होता है तो वेलोसिटी भी कांस्टेंट हो जाती है और इसको कहते हैं टर्मिनल वेलोसिटी. मोशन ग्राफ्स 3 किस्म के हैं. मोशन ग्राफ्स में बेसिकली जो काइनेमेटिक क्वांटिटीज़ होती हैं उनको टाइम के साथ रिलेट किया जाता है. यू कैन रेफर टू दीज. सो टाइम ग्राफ में इट कैन बी डिस्प्लेसमेंट टाइम या फिर डिस्टेंस टाइम ग्राफ. बेसिकली पोजीशन टाइम ग्राफ्स होते हैं. इन दोनों में फ़र्क ये है कि डिस्प्लेसमेंट जो है दैट्स अ वेक्टर क्वांटिटी, डिस्टेंस इज़ अ स्केलर क्वांटिटी. डिस्प्लेसमेंट में वेलोसिटी वो जो है मैग्नीट्यूड और डायरेक्शन होता है, लेकिन डिस्टेंस में you've only got magnitude, no direction. तो जो ग्रेडियंट्स होते हैं पोजीशन टाइम ग्राफ्स के वो हमें वेलोसिटी या स्पीड देते हैं मूविंग ऑब्जेक्ट के. तो यू कैन रिफर टू दिस. पोजीशन टाइम ग्राफ्स में ये कांस्टेंट है लाइन एंड इट्स गॉट अ जीरो ग्रेडियंट. दैट मीन्स द ऑब्जेक्ट इज स्टेशनरी क्योंकि टाइम बढ़ता जा रहा है और डिस्प्लेसमेंट जीरो है. यूनिफॉर्म स्पीड में द ग्रेडियंट इज कांस्टेंट एंड द लाइन इज कांस्टेंट. देयर आर नो मतलब लाइन टेढ़ी मेढ़ी नहीं है और इट्स यूनिफॉर्म स्पीड ना इंक्रीज हो रही है ना डिक्रीज हो रही है, इट्स अ स्ट्रेट लाइन. नॉन यूनिफॉर्म स्पीड में इट्स अ कर्व लाइन. इसका ग्रेडियंट कैलकुलेट करने के लिए यू कैन ड्रॉ टेंजेंट. वेलोसिटी टाइम ग्राफ्स या तो स्पीड टाइम या वेलोसिटी टाइम हो जाता है. फ़र्क यही है कि स्पीड एक स्केलर क्वांटिटी है और वेलोसिटी एक वेक्टर क्वांटिटी है. वेलोसिटी टाइम ग्राफ का जो ग्रेडियंट है वो हमें एक्सेलरेशन देता है और जो डिस्प्लेसमेंट होता है या फिर डिस्टेंस होता है जिसके जो ऑब्जेक्ट होते हैं बेसिकली जो ट्रैवल कर रहा होता है ग्राफ में, उसका जो डिस्प्लेसमेंट डिस्टेंस होता है वो हम ऐसे कैलकुलेट कर सकते हैं कि हम इन ग्राफ्स के नीचे जो एरिया है वो कैलकुलेट करते हैं. ये कुछ क्वेश्चंस हैं. स्केचिंग डिस्प्लेसमेंट टाइम ग्राफ्स. द ग्रेडियंट ऑफ डिस्प्लेसमेंट टाइम ग्राफ इज वेलोसिटी. Therefore, speed is the rate of change of distance, or v equals to dx over dt. X equals to f v dt. In other words, distance is the area under the speed time curve, like I just explained. Up, the given curve is a velocity time curve with origin at the top left corner, but the speed time curve would simply reflect the velocity time curve in the time axis. जैसे वेलोसिटी नेगेटिव है, स्लोप जो है डिस्प्लेसमेंट टाइम ग्राफ का वो भी नेगेटिव होगा. सो इनिशियली एट लोवेड वेलोसिटीज द एरिया अंडर द कर्व इज स्मॉल एंड इंक्रीजेस स्लोली, जबकि हाई वेलोसिटीज पे एरिया कर्व लार्ज होता है और रैपिडली इंक्रीज हो रहा होता है. जब टर्मिनल वेलोसिटी हासिल कर ली जाती है वेलोसिटी कांस्टेंट होती है और रेट ऑफ चेंज ऑफ डिस्प्लेसमेंट इज कांस्टेंट, जैसे कि इस स्केच में शो हो रहा है. स्केचिंग एक्सेलरेशन टाइम ग्राफ्स. Acceleration is simply the rate of change of velocity change or the gradient of the velocity time sketch. The gradient is minus 9.81 meters per second square when velocity is 0 meters per second and increases until it reaches 0 when terminal velocity is reached due to air resistance. जब एक ऑब्जेक्ट का वेलोसिटी इंक्रीज करता है या डिक्रीज करता है लीनियरली, जो ग्रेडियंट होता है वो कांस्टेंट होता है, जिसकी वजह से यूनिफॉर्म एक्सेलरेशन या फिर डिसेलरेशन दिखाई जा रही होती है. सिमिलरली अगर उसकी वेलोसिटी इंक्रीज होती है या डिक्रीज होती है नॉन लीनियरली, द एक्सेलरेशन इज नॉन यूनिफॉर्म, जैसे आपको यहाँ पे नज़र आ रहा है. इट्स नॉन यूनिफॉर्म, इट्स कर्व्ड. वर्टिकल मोशन ग्राफ में एक्सप्लेनेशन है कि ग्राफ 1 इज द वेलोसिटी टाइम ग्राफ फॉर द मोशन ऑफ पार्टिकल प्रोजेक्टेड वर्टिकली अपवर्ड्स। आप ये नोटिस करेंगे कि ग्राफ नेगेटिव में जाता है, ये क्योंकि जब पार्टिकल मैक्सिमम हाइट में चल जाता है इट स्टार्ट्स रिटर्निंग डाउनवर्ड्स, जिसकी वजह से वेलोसिटी वो जो है वो बढ़ती जाती है लेकिन नेगेटिव डायरेक्शन में। The time at which the particle reaches its maximum height can be found by checking where the graph intersects the time axis, because at that point the velocity is 0 meters per second. Graph 2 shows a particle moving with constant acceleration as the slope is constant. Graph 3 shows the motion of a ball dropped and bouncing back. The velocity increases with a constant gravitational acceleration as the ball is released. As the ball hits the ground, which is at this point, and bounces back, the direction of velocity changes, it becomes negative, hence the sudden dip in the graph. लेकिन फिर जो है velocity decrease करना शुरू हो जाती है। इस example में the downward direction is taken as positive. Graph 4 shows a particle moving with a constant deceleration as the velocity is decreasing linearly. Equations of motion में acceleration is constant, motion is in a straight line. अब आ जाती है हमारी 4 equations of motion. Assumptions. 4 equations of motion. S is equal to Vi plus Vf over 2 whole square multiplied by t. Vf equals to Vi plus At. Vf equals to Vi plus At. और third है S equals to Vit plus 1 over 2 At square. 4 is Vf square equals to Vi2 plus 2As. S इनमें जो आपके वेरिएबल्स हैं, S is displacement, A is acceleration, Vs is your initial velocity, Vf is your final velocity, and T is your time. ये एक वर्ड एग्जांपल है. You can check this out. It will help you with better comprehension. अब आ जाते हैं. By the way, you need to know your derivations as well. Make sure you learn your derivations for the 4 equations. अब आ जाते हैं Newton's law of motion. First law है an object continues in its state either of rest or motion unless a force is applied to change its state. Second law है the linear momentum of an object changes with the rate proportional to the net force, which is proportional to the mass and acceleration of the object. P over D equals to F equals to ma. P जो है वो linear momentum होता है, F force होता है, m denotes mass and a denotes acceleration. Third law, if a body A applies a force F1 on a body B, then body B applies a force F2 which is equal to negative F1 as it's in the opposite direction on the body A. Hence the force applied by body B on body A is equal in magnitude but opposite in direction. Law of conservation of momentum, the total linear momentum of an isolated system remains constant. According to law of conservation of momentum, जो total momentum होता है before collision वो after collision भी same होता है. m1u1 plus m2u2 equals to m1v1 plus m2v2. You can refer to this image. Examples of law of conservation of momentum, ये जैसे rocket propulsion होता है या फिर gun और bullet system होता है. Momentum or collisions. The type of collision determines whether the kinetic energy of the bodies in a system is conserved or not. दो किस्म के collisions होते हैं, elastic और inelastic. Basically, जब kinetic energy constant नहीं रहती collision में, वो inelastic होता है. And जब collision constant रहती है, तो that's an elastic collision. You can refer to these graphs and these equations. अब आप कंसिडर करें दो स्मूथ नॉन रोटेटिंग बॉल्स हैं जो नहीं घूम रही, मास m1 और m2, जो वेलोसिटी v1 और v2 से सेम डायरेक्शन में जा रही हैं. दो एक दूसरे से कोलाइड करती हैं और उनके कोलिजन के बाद वेलोसिटी हो जाती है v1 v2, which is given by this equation. You can refer to this. Make sure to memorize all of them. Final velocities of m1 and m2 are collision. Basically, inelastic collisions में the colliding bodies lose some of the kinetic energy in the form of other energies such as heat. Road accidents between vehicles are inelastic as most of the energy is lost as heat, sound, and to damage the vehicles involved in the collision. In a perfectly inelastic motion, the colliding bodies stick together and move as a single unit of the collision. When a force acts on an object for a short amount of time, impulse is the measure of how much the force changes the momentum of an object. Impulse का formula होता है force multiplied by time. Change of time equals to final time minus initial time. The ball at rest gains the velocity of the colliding ball, while the ball initially with the velocity you want comes to rest. क्योंकि impulse measure है कि किस तरह momentum change करते हैं as a result of force acting on it for a period of time. An alternative formula for impulse looks like this. This formula relates impulse to the change in the momentum of the object. Impulse has two different units, either kilograms times meters per second या फिर newtons times seconds. Distance time graph. अगर एक बॉडी इक्वल डिस्प्लेसमेंट्स कवर करती है इक्वल टाइम में, जितना भी छोटा हो जो बॉडी है, इट्स सेड टू हैव यूनिफॉर्म वेलोसिटी. वेरिएबल वेलोसिटी एज यू कैन सी इट्स नॉट कांस्टेंट, इट्स कर्व्ड. अगर ये एक बॉडी अनइक्वल मतलब नॉट इक्वल डिस्प्लेसमेंट्स कवर करती है लेकिन इक्वल इंटरवल्स ऑफ टाइम में जितने भी छोटे हो, तो बॉडी इज सेड टू हैव वेरिएबल वेलोसिटी. Projectile. When a body is thrown upward making a certain angle q with the horizontal direction and moves freely with the action of gravity, it is called a projectile. The path followed by a projectile is called its trajectory and is confined to a vertical plane. The trajectory of a projectile is usually a parabola. Such motion of the object is called projectile motion. Note that the horizontal component of the velocity during projectile motion does not change, whereas the vertical component is influenced by gravity. The vertical and horizontal components of the motion can be treated separately for analyzing the projectile motion, and the corresponding equations of motion can be applied. Velocity of projection. Consider a projectile launched at an angle theta with x-axis. The x and y components of initial velocity of projectile are Viz equals to Vi, which is your initial velocity, multiplied by cos theta, या फिर Viy is equal to your initial velocity multiplied by sin theta. The horizontal acceleration of projectile is 0, ax equals to 0. The vertical acceleration of projectile is gravitational acceleration, which is 9.81. No acceleration along x-axis, hence no change in velocity for horizontal component. The horizontal component of velocity remains constant. The vertical component of velocity linearly because of uniform acceleration. Time of flight. जो time of flight होती है वो होता है वो वक्त which the time the projectile takes to cover the distance from its place of projection to the place where it hits the ground. It's called a time of flight. जैसे यहाँ से लॉन्च हुआ है और यहाँ पे लैंड हुआ है, तो जितने देर में ये लैंड हुआ है, that's called the time of flight. You can get this via this formula, which is 2 times initial velocity times your sin theta, and all of this over g. Range of the projectile. Maximum distance which a projectile covers in the horizontal direction is called the range of the projectile. It depends upon the velocity of projection and the angle of projection. Range of projectile equals to Vi square sin 2 theta over g. A projectile covers maximum horizontal distance when it is projected at an angle of 45 degrees. This is called the maximum range of the projectile. R max equals to V2I over g. V square I over g. Maximum height of the projectile. The maximum height reached by the projectile is called as the height of projectile, which is V square I, your initial velocity, sin square theta over g. The time of flight is the time taken by the projectile to cover the distance from the place of its projection to the place where it hits the ground. T equals to 2t, which is equal to 2v sin theta over g. Range of the projectile. The maximum distance which a projectile covers in the horizontal direction is called the range of the projectile. It depends upon the velocity of projection and the angle of projection. R equals to Vx multiplied by your time of flight. V cos theta equals to basically multiplied by 2v sin theta over g in brackets equals to v squared sin 2 theta over g. Projectile covers maximum horizontal distance when it is projected at an angle of 45 degrees. This is called the maximum range of the projectile. R max equals to v squared over g. Alright, so our topic for today is waves. A wave is a disturbance in a medium that transfers energy from one point to another without transporting matter. Waves के दो मेन जो टाइप्स हैं वो हैं मैकेनिकल और इलेक्ट्रोमैग्नेटिक. मैकेनिकल वेव्स में उनके प्रोपेगेशन के लिए they need a medium, whereas इलेक्ट्रोमैग्नेटिक वेव्स को मीडियम की ज़रूरत नहीं होती उनके प्रोपेगेशन के लिए. An example of an electromagnetic wave is X-rays, whereas sound waves and water waves are examples of mechanical waves. Wavelength is distance between two successive phase points. दो पॉइंट्स फेज में हैं अगर उन पॉइंट्स के बीच में एक पूरी वेव है. Examples include two successive wave crests or throws. Wave fronts are lines joining points of same state of vibrations. A line joining crests or a line joining throws. The speed with which the wave travels in its direction of motion is called wave speed and is given by v equals to f lambda, where f is the frequency of the wave and lambda is its wavelength, measured in meters. The velocity of sound in air is dependent upon the density of the medium rather than the pressure. Amplitude is the maximum displacement from the mean position. Progressive waves. Waves which transfer energy by moving away from the source of disturbance are known as progressive waves. Ripples generated in water by dropping a pebble are an example of a progressive wave. Two kinds of progressive waves are longitudinal and transverse. Longitudinal waves are those that oscillate parallel to the propagation or motion of the waves. Sound waves are always longitudinal. Longitudinal waves have areas of compression and rarefaction, regions where particles are closest and farthest, respectively. Transverse waves are those that oscillate perpendicular to the propagation of waves. Water waves and waves on strings when vibrated are transverse. Periodic wave. It's a wave with a continuous repeating pattern which determines its wavelength and frequency. It is characterized by the amplitude, a frequency, and a period. Amplitude wave is directly related to the energy of a wave. It also refers to the highest and lowest point of a wave. As you can see, these are rarefactions and these are compressions, where respectively the distance between molecules is larger and shorter. This is a throw, the lower part where the displacement is maximum negative, and a crest where the displacement is maximum positive. An amplitude, which is the maximum displacement of a particle from its equilibrium position. Superposition. If n waves passing through a medium gives displacement y1, y2, y3, yn to particles of the medium, then the net displacement y is given by y equals to y1 plus y2 plus y3 plus minus yn. When two waves act upon a particle simultaneously, then three different phenomena are observed under different circumstances. Interference. When two waves have the same frequency and are traveling in the same direction. Beats. When two waves of slightly different frequencies are traveling in the same direction. And stationary waves, where two waves of equal frequencies are traveling in the opposite direction. Interference of sound waves. The superpositioning of two waves having same frequency and traveling in the same direction results in a phenomenon called as interference. When the path difference is an integral multiple of wavelength, the two waves are added up. This effect is called a constructive interference. Path difference equals to n lambda, n equals to 0, plus minus 1, plus minus 2, plus minus 3. When the path difference is an odd integral multiple of half wavelength, the two waves cancel each other. This effect is known as constructive interference. Stationary wave. Waves that have a constant position are called stationary waves or standing waves. Interference and superimposition of two or more waves traveling in opposite directions lead to formation of standing waves. As an example, if a string is tied to a wall and vibrated up and down, and the wave formed on the string reflects from the wall and interferes with the incoming waves, a stationary wave is produced. Stationary waves have points of permanent zero displacement called nodes. As you can see, this is where the displacement is zero. And points of maximum amplitude called antinodes. These are marked by A, where the displacement is maximum. Interference in stationary waves. Particles on waves can interfere in two ways. destructively or constructively. Destructive interference is the superposition leading to zero displacement. Hence, a crest interfering with a trough would interfere destructively, leading to the resultant wave having zero displacement at that point. Nodes are points of completely destructive interference, as they have zero displacement, while antinodes are points of completely constructive interference, as they have maximum displacement. At nodes, the interfering waves are out of phase from each other by pi radians. At antinodes, the interfering waves are in phase with each other since the amplitudes of the interfering waves add up to give a resultant wave with a larger amplitude than any of the incident waves. It is important to note that in standing waves, no transfer of energy occurs, as in progressive waves, and the positions of antinodes and nodes stay the same as the wave doesn't move with time. Harmonics. Consider a string tied at both ends. The string can vibrate at specific wavelengths as it must form nodes at both tied ends. The first harmonic or fundamental frequency is when the wavelength of the standing wave is twice the distance L as shown. So for the first harmonic wavelength, lambda 1 equals to 2L, and for the second one, lambda 2 equals to L. You can use these formulas to calculate the frequency of these harmonics. Note that for a standing wave to form, in this case, the ends must have nodes because of the specificity of the wavelengths that can fit in the distance L. Characteristics of simple harmonic motion. The acceleration of particles is directly proportional with displacement and directed towards its mean position. The total energy of a particle exhibits simple harmonic motion is conserved. Simple harmonic motion can be represented by harmonic function of sine or cosine. Velocity of a body executing simple harmonic motion is maximum at mean position and zero at extreme position. Acceleration of a body executing simple harmonic motion is maximum at extreme position and minimum at mean position. Instantaneous displacement. The expression for instantaneous displacement x equals to x naught sine omega t. Displacement is maximum at extreme position. Instantaneous velocity. The expression for it is v equals to omega under root x naught square minus x square. Instantaneous acceleration. The expression for instantaneous acceleration is a equals to negative omega square x. Standing waves in various scenarios. Pipe. If we take a windpipe with one end open and the other end closed, the following standing wave patterns are observed depending on the wavelength of the sound wave used to produce the pattern. The first harmonic shows a quarter standing wave, hence L equals to 1 over 4 lambda 1. For second harmonic, L equals to 3 over 4 lambda 2, and so on. These harmonics actually show the motion of the air in the tube. The antinodes formed at the open end show that the air can move back and forth at the open end, but not at the closed end. Fundamental frequency equals to F1 equals to V over 2L. Frequency of nth harmonic equals to Fn equals to Nv over 2L. If both ends of the pipe are open, antinodes would form at both ends, and the wavelength for first harmonic would simply be given by L equals to 1 over 2 lambda 1. Fundamental frequency equals to V over 4L. For nth harmonic, Nv over 4L. 1, 3, 5. Water tube. If you take a tube filled with water so that the length of the air column can be varied by draining water from the tube, the tuning fork resonates the air column at specific frequencies, I guess. Doppler's effect. This phenomenon is described as the change in frequency of a wave with respect to an observer who is moving relative to the wave source. From the diagram above, we can see that as the wave source moves closer to the observer, the frequency of the sound heard by the observer decreases. Conversely, when the wave source moves away from the observer, the frequency of the waves decreases. A listener moving towards a stationary source of sound. A source of sound having frequency f is at rest, but the listener is moving with velocity v towards source. If v is the velocity of sound, then the apparent frequency f of the sound heard by the listener will be f equals to v plus b multiplied by f over v. So the pitch of the sound heard by the listener will be increased. A source of sound moving towards a stationary listener. A source of sound having frequency f is moving with velocity a towards a stationary listener. If v is the velocity of the sound, the apparent frequency f of the sound heard by the listener will be vf over v minus a. Thus, the pitch of sound heard by the listener is increased. A source of sound is moving away from the listener at rest. A source of sound having frequency f is moving with velocity a towards a stationary listener. If v is the velocity of sound, then the apparent frequency of the sound heard by the listener will be vf over v plus a. Therefore, the pitch of the sound heard by the listener will increase when the source is moving away from the source. A listener is moving away from a source at rest. A source of sound having frequency f is at rest, and the listener is moving with velocity v away from the source. If v is the velocity of sound, then apparent frequency f of the sound can be heard by the listener will be v plus b multiplied by f over v. Thus, the pitch of sound heard by the listener is increased. Beats. When two bodies of slightly different frequencies are sounded together at the same time, the periodic alternations of sound between maximum and minimum loudness are called beats. In basic terminology, which you should know, oscillatory motion, regular, periodic to and fro motion is called oscillatory motion. Examples include an oscillating loaded spring and simple pendulum. Simple harmonic motion is motion in which the acceleration is directly proportional to the displacement and always directed towards the mean position. Examples include simple pendulum mass spring system. Equilibrium position is the position where the object undergoing the oscillations are stationary before the force was applied to bring about their motion. Its motion. The displacement of the object is taken to be zero at equilibrium position. The maximum displacement from the mean or equilibrium position is called the amplitude. One complete cycle is the journey of the pendulum from position 1 to 2 and then back to position 1. The time taken to cover one cycle is called the time period. For a simple pendulum, t equals to 2 pi under root L over g. For a mass spring system, t equals to 2 pi under root m over k. Frequency is the number of cycles per second and it's measured in hertz. Alright, so our topic for today is physical optics. So interference of light is when two or more waves overlap each other. There is a resultant wave with greater amplitude. Constructive interference is when at any point the waves are in phase, मतलब कि एक wave का crest दूसरे wave के crest पे आता है या फिर एक wave का throw दूसरे के throw पे आता है, तो there is an increase in amplitude. डिस्ट्रक्टिव इंटरफेरेंस कहते हैं जब दो वेव्स आउट ऑफ फेज है, मतलब एक का क्रेस्ट दूसरे के ड्रॉ पे आता है, तो देयर इज अ डिक्रीज इन द रिजल्टेंट एम्पलीट्यूड. तो कुछ कंडीशंस हैं डिटेक्टेबल इंटरफेरेंस की. द सोर्स शुड बी मोनोक्रोमैटिक, दैट इज ऑफ सिंगल वेवलेंथ. द सोर्सेज शुड बी कोहेरेंट, मतलब कि दे शुड बी डिराइव्ड और स्प्लिट इनटू टू फ्रॉम द सिंगल सोर्स ऑफ लाइट. द ट्रू जो दो सोर्सेज हैं उनको इकट्ठे मतलब करीब होना चाहिए एक दूसरे के, or the principle of linear superposition should be applicable. So Young's double slit experiment. For a bright fringe, d sin q equals to ml. For dark fringe, sin q equals to m plus 1 over 2 multiplied by l. The distance between two adjacent bright or dark fringes changes in y equals to lambda l over d. So diffraction of light and diffraction grating. A diffraction grating consists of a glass plate on which very fine equidistant parallel lines are drawn by means of a fine diamond point. The lines act as an opaque through which the light cannot pass, while the spacing between the lines acts as a slit through which light can pass. A typical diffraction grating has about 400 to 5000 lines per centimeter to produce diffraction of light. Usually grating may have as many as 12,000 lines per centimeter to produce diffraction of light. The spacing d between the centers of adjacent lines is called the grating element. If n is the number of lines in a unit length of diffraction grating, then grating element d equals to 1 over n. Polarization. It's the property of transverse waves which governs the geometric orientation of the wave and how it's propagated. Newton rings. Newton's rings are circular fringes formed due to interference in a thin air film enclosed between a convex lens and a flat glass plate. Interference in thin films. In our daily life, there are many examples in which we see the interference produced in thin films. Some of the examples are colored fringes formed in soap bubbles, in thin layers of oil on water or other liquids, and in cracks in a glass plate. The different colors which are seen with ordinary white light is produced due to interference of waves reflected from the opposite surface of the film. Michelson's interferometer. The interferometer, invented by an American physicist, A. Michelson, from 1852 to 1931, was named as Michelson interferometer. It is an instrument which is used for the accurate measurement of wavelength and precise length measurements. Its working principle is based on interference. When a light beam falls on it, it splits the light beam into two parts and then recombines them to produce an interference pattern after they have traveled over different paths. Optical fibers. They're used nowadays in communication systems to transmit data at high speeds using light as a carrier. The optical fiber consists of a long, flexible glass core with a high refractive index. This core is surrounded by a cladding having lower refractive index than that of the core, so that total internal refraction can take place. The following diagram shows the optical fiber. Here's the cladding, the core, the normal, and theta I, and theta R, and theta S. Alright, so our topic for today is oscillations. इस टॉपिक में आपको फॉलोइंग कॉन्सेप्ट्स आने चाहिए: सिंपल हार्मोनिक मोशन, ऑसिलेटरी मोशन, रेगुलर periodic to and fro motion is called oscillatory motion. Objects और particle जो कि oscillatory motion undergo करते हैं, हम उनको कहते हैं कि वो simple harmonic motion में है. Examples include an oscillating loaded spring and simple pendulum. Equilibrium position is the position where the object undergoing the oscillations was stationary before the force was applied to bring about its motion. The displacement of the object is taken to be zero at equilibrium position. The maximum displacement from the mean or equilibrium position is called the amplitude. One complete cycle is the journey of the pendulum from position 1 to 2 and then back to position 1. The time taken to cover one cycle is called the time period. Frequency is the number of cycles per second. इसका unit hertz होता है. Period, which is t, is equal to 1 over f. Conditions for simple harmonic motion. अगर ये दोनों conditions होती हैं तो एक object simple harmonic motion में होते हैं. अगर उसकी जो acceleration है उसकी displacement from mean position से directly proportional है and equilibrium से, और दूसरा उसकी एक्सेलरेशन हमेशा इक्विलिब्रियम पोजीशन की तरफ ही डायरेक्टेड होनी चाहिए. अगर हमने चेक करना ना कि अगर एक बॉडी हार्मोनिक मोशन में है, सिंपल हार्मोनिक मोशन में या नहीं, हम एक्सेलरेशन को इसमें देखते हैं. a इक्वल्स टू माइनस ओमेगा स्क्वायर x. तो ये आ गया आपका डायग्राम. This is the point of suspension and this is the length from the point of suspension to the bob. This is the position 1 and position 2. This is your equilibrium position in which the bob was stationary before the force was applied, and this is your amplitude. Here you go. This is a displacement and period graph. This is t over 2, t, 3t over 2, 2t. This is your amplitude, which is your maximum displacement from your mean position. Equilibrium position, sorry. Consider the displacement during the motion of a pendulum. Consider the displacement during the motion of a pendulum. The pendulum starts from position 1 in the figure at the maximum displacement and reaches its equilibrium point or zero displacement. Then the bob travels towards position 2, which again has maximum magnitude of displacement, but it's in the opposite direction of position 1, hence negative displacement. At points 1 and 2, the bob becomes stationary instantaneously before changing its direction. Notice that the above graph shows the displacement starting from the position of maximum displacement rather than from zero displacement. Hence, the graph is a phase shifted sine curve with a period of 2 pi with equation x equals to x naught sine omega t plus phi, where x naught is the amplitude or the maximum displacement, omega is the angular frequency given by omega equals to 2 pi over t, and phi is the phase shift, which in our case is pi over 2 since the bob starts from maximum displacement x naught. Velocity. The gradient of a displacement time graph gives the velocity at any point, as velocity is the rate of change of displacement. V equals to dx over dt. Hence, we can simply differentiate the equation of displacement to gain the equation of velocity. V equals to dx over dt, which is equal to omega x naught cos omega t plus phi. This is the same graph we saw above. This is your velocity period graph, and we saw this earlier as well. The velocity graph is defined by a phase-shifted cosine curve because in our case the motion has been considered from the position of maximum displacement, and at maximum displacement the velocity is 0 as shown by the graph, which corresponds to the displacement time curve above. Note that the sine and cosine functions have a maximum value of 1, hence the maximum value of velocity is Vmax equals to omega x naught. Acceleration. The gradient of a velocity time graph gives acceleration, as acceleration is the rate of change of velocity. A equals to dv over dt, hence derivate v equals to omega x naught cos omega t with respect to time. dv over dt equals to minus omega square x naught sine omega t plus phi. Because of the negative sign with the sine curve, the graph of acceleration time would simply be the reflection of displacement time curve in the horizontal time axis. The magnitude of the maximum value of acceleration is given by max acceleration equals to omega square x naught. Velocity and acceleration with respect to displacement, velocity displacement graph. The magnitude of velocity is maximum when the bob passes through the equilibrium position, and 0 when the bob is at the positions of maximum displacement. The sign convention must be kept in mind because we are dealing with vectors. When the bob passes through the equilibrium position, the velocity can have either negative direction or positive depending on the direction it is traveling in, but the magnitude is constant. Vmax equals to omega x naught at zero displacement. So at zero displacement जो velocity वो या तो omega x naught हो सकती है या negative omega x naught. At displacement of x naught and minus x naught, velocity 0 होती है. The following graph shows the variation of velocity with the displacement. As x naught decreases, omega x naught, it's basically circular. If we are required to calculate velocity in positions other than the position of maximum or zero displacement, we can find the velocity by using the following formula. V equals to plus minus omega under root x naught square minus x square. Acceleration displacement graph. Magnitude of acceleration is maximum when the magnitude of displacement is maximum, and 0 when the displacement is 0. The following graph shows the variation of acceleration with this displacement from mean position. So as we can see, as x naught increases, the value of a basically it goes on negatively. It's called a negative gradient. As the graph is a straight line with constant negative gradient, the following relation between acceleration and displacement can be derived from the graph. A equals to omega square minus negative omega square x. Loaded spring system in simple harmonic motion. It is assumptions for simple harmonic motion. The mass of spring is negligible. The spring obeys Hooke's law, matlab कि elastic limit is not crossed. The amplitude of vibrations must be lesser than the equilibrium extension. Consider a vertical massless spring loaded with a mass m. A vertical massless spring loaded with a mass m bringing about an extension of E. When the mass is pulled by displacement x to bring about oscillations in the springs, the new total extension is E plus x. The forces can be solved in the vertical direction to derive relation between time period t and mass, or between time period and extension. You can refer to these graphs. We know that in figure B, when the system is in equilibrium, the vertical forces are balanced. Hence, mg equals to ke. In figure C, the resultant of the vertical forces causes the acceleration of the mass, hence F equals to ma. Mg minus k E plus x equals to ma. Substituting mg into ke, mg equals to ke, ke minus kx equals to ma, a equals to minus k over mx. क्योंकि स्प्रिंग सिंपल हार्मोनिक मोशन में है, acceleration a is the form of a equals to negative omega 2x to the power 2x, I guess. A equals to negative omega to the power 2x, omega square equals to k over m, omega equals to under root k over m. Using we used omega equals to 2 pi over t. Period t equals to 2 pi, t equals to 2 pi under root m over k, and this is also equal to 2 pi under root e over g, since mg is equal to ke. These are multiple spring patterns, spring systems, series and parallel basically. Here you've got a singular thing. Here's F2, K1 and K2 basically. Spring constant K 1 over K series में basically जो spring constant होते हैं वो होता है 1 over K equals to 1 over K1 plus 1 over K2, जबकि parallel में होता है K equals to K1 plus K2. Force applied इसमें F equals to F1 और equals to F2, लेकिन इसमें F equals to F1 plus F2. Extension in series is x equals to x1 plus x2, and in parallel में x is equal to x1 and is also equal to x2. Motion of a simple pendulum. Suppose a pendulum is made to oscillate with a small angle theta. We can resolve forces and apply Newton's second law to prove that the pendulum is indeed in simple harmonic motion. Taking the right direction as positive, the component of weight contributing to the motion of the bob is given by minus mg sin theta. This is theta, this is L, this is T. Figure 7, force on bob of simple pendulum. The negative sign, it shows that the force acting on the bob is accelerating it towards the equilibrium position. Hence, applying Newton's second law, F equals to ma equals to negative mg sin theta, a equals to negative g sin theta. Hence, we assume that the value of theta is small. We can approximate sin theta to sin theta equals to x over L, where x is the bob's displacement from its mean position and L is the length of string bob it's attached to. A equals to negative g x over L. A is also equal to negative x g over L. Sorry. Hence, we have shown that the acceleration is of the form a equals to negative omega square x, where g over L equals to omega square. G over L equals to omega square 2 pi over t square equals to g over t, which is also equal to t equals to 2 pi under root L over g. Arrow basically. Looking at the formula, it can be noted that the time period of the pendulum is independent of the mass of the bob as well as the amplitude of oscillation. Rather, it is only dependent on the length of the pendulum. Energy conservation. Simple harmonic motion में जो energy है oscillating body की वो kinetic और potential के बीच में cycle होती रहती है. अगर एक oscillating body external forces से नहीं affect होती तो body की जो total energy है system की वो constant रहती है, which is the sum of the kinetic and potential energies. So total energy E equals to k plus u, which is equal to which is constant. When a mass is displaced from a spring, it has minimum potential energy when it passes through its equilibrium potential, while the kinetic energy at that point is maximum. When the mass reaches position of its maximum displacement, it comes instantaneously to rest. Hence, minimum kinetic energy while maximum potential energy at maximum displacement. The total sum of these energies always stays constant. Total energy equals to 1 over 2 m omega square x naught square. Total energy of the system. So here you can see kinetic energy and potential energy. They're always equal at any point in the graph. They're always constant basically. Not equal, constant. The total energy of the system. Kinetic energy equals to 1 over 2 mv square, but v equals to plus minus omega under root x naught square minus x square. Kinetic energy equals to 1 over 2 m omega square multiplied by x naught square minus x square. Kinetic energy maximum होती है जब x 0 होता है, तो इसकी वजह से maximum kinetic energy is equal to 1 over 2 m omega square x naught square. So consider SHM in an oscillating spring to find the potential energy in terms of displacement x. Potential energy U equals to 1 over 2 kx square, k equals to m omega square, k equals to m over omega to the power 2, U equals to 1 over 2 m omega square x square. At x equals to 0, the potential energy U equals to 0. So the total energy at x equals to 0 is the sum of the kinetic energy and potential energy. E equals to 1 over 2 m omega square x naught square. It can be intuitively said that at maximum displacement the kinetic energy will be 0 and the potential energy U equals to 1 over 2 m omega square x naught square, क्योंकि टोटल एनर्जी कांस्टेंट है. जो दूसरे कॉन्सेप्ट्स हैं जिनके बारे में आपको अवेयर होना चाहिए वो है रेजोनेंस, फ्री ऑसिलेशंस और डैम्प्ड ऑसिलेशंस. Alright, so our topic for today is atomic spectra. Spectroscopy is the branch of physics that deals with the investigation of wavelengths and intensities of electromagnetic radiations emitted or absorbed by atoms. There are three types of spectra: continuous spectrum, band spectrum, and discrete or line spectrum. In atomic spectra, the spectrum of the electromagnetic radiation emitted or absorbed by an electron during transitions between different energy levels within an atom. Energy levels and excitation. Electrons in an atom can only definite or discrete energy. Values are known as energy levels. Here you can see excitation, where n2, 3, 4, and it goes up to infinity, I guess. And here is emission, where it goes from 2 to 1. You can also see these values. It can be observed from this energy level diagram that as we move to higher states of n, the difference between successive energy levels decreases. Excitation is defined as the movement of electrons from lower to higher energy states. It can be achieved by bombarding the electron with a lower energy state with an incident electron which has a higher kinetic energy within the energy gap between the levels, for which we need to excite. Ke is greater than delta E. Excitation can also be achieved by making the electron absorb an incident photon whose energy is exactly equal to the energy gap. In other words, the energy required for excitation is simply equal to the energy gap. Excitation potential, or the minimum potential required to excite the electron, can be calculated by simply dividing the excitation energy by the charge of an electron. U equals to negative 13.6 eV over n square. Electron transition. Emission is the transition of an electron from a higher to a lower energy level. During this transition, a photon is released whose energy is equal to the energy gap. HF equals to EF minus EI. F equals to EF minus EI over H, where EF is the final energy and EI is the initial energy of the electron. As the values of final energy and initial energy are discrete because of discrete energy levels, the values of frequency of the photon release are also discrete. Hence, a line spectrum is produced which only shows specific values of frequency rather than a continuous spectrum. Hydrogen emission spectrum. Suppose that the electron in a hydrogen atom is in an excited state with the energy En and make a transition to a lower state P with energy Ep, where Ep is greater than En. Then HF equals to En minus Ep. HF equals to negative E0 multiplied by 1 over n square minus 1 over p square. 1 over lambda equals to E0 over Hc multiplied by 1 over p square minus 1 over n square. 1 over lambda equals to Rh multiplied by 1 over p square minus 1 over m square. Rh equals to 1.0974 x 10 times 10 to the power 7 per meter. Lyman series. 1 over lambda equals to Rh multiplied by 1 over 1 square minus 1 over n square. Lyman series lies in the UV region. Balmer series 1 over lambda equals to Rh multiplied by 1 over 2 square minus 1 over n square, and the Balmer series lies in visible region. Paschen series lies in IR region. The formula is 1 over lambda equals to Rh multiplied by 1 over 3 square minus 1 over n square. And the Packet series, which lies in the IR region, the formula for it is 1 over lambda equals to Rh multiplied by 1 over 4 square minus 1 over n square. For the Fun series, 1 over lambda equals to RH multiplied by 1 over 5 square minus 1 over n square, and the fun series lies in the IR region. Emission and absorption spectrum. Emission line spectrum consists of bright lines on dark background because of transition of electrons from higher to lower energy levels. Absorption spectrum consists of a continuous bright spectrum intersected by dark lines. The spectrum can be produced by passing white light through cold gas, because in cold gas electrons absorb photons of specific frequencies, getting excited and then they re-emit in all directions. Emission spectrums form the basis of formation of some common spectrum groups of transitions or series, including Lyman series, Balmer series, and Paschen series. You can check this out. Here there's hot gas and there's cold gas. You can see the spectrums respectively. Bohr's model of the hydrogen atom. An electron bound to the nucleus in an atom can move around the nucleus in certain circular orbits without radiating energy. These orbits are called the discrete stationary states of the atom. Only those stationary orbits are allowed for which orbital angular momentum is equal to an integral multiple of h over 2 pi. An example, MVR equals to NH over 2 pi, where N equals to 1 over 3, 1 to 3, and so on, and N is called the principal quantum number. M and V are the mass and velocity of the orbiting electron respectively, and H being Planck's constant. Wherever an electron makes a transition, that it jumps from higher energy state En to a lower energy state Eb, a photon of energy hf is emitted, so that hf equals to En minus Eb, where f equals to C over L is the frequency of the radiation emitted. De Broglie's interpretation of Bohr's orbits. According to de Broglie's hypothesis, L equals to 2 pi r over n, or mr equals to n 2 pi. Quantized radii, Vn equals to 2 pi ke square over nh. Quantized energies, En equals to negative 4 over n square multiplied by 2 pi square k square me to the power 4 over h square. This is equal to negative E naught over n square, where EO equals to 2 pi square k square me to the power 4 over h square, and it's equal to negative 13.6 eV. Hydrogen emission spectrum and Rydberg constant. 1 over lambda equals to RH multiplied by 1 over p square minus 1 over n square, where RH is the Rydberg constant given by the equation RH equals to E naught over Hc, which is equal to 1.0974 times 107 per meter. X-rays. When a charged particle decelerates, electromagnetic radiations are produced. The X-rays are called Bremsstrahlung radiations. If a particle knocks out an inner electron, then an outer electron comes to take its place. The difference in the energy of the two levels is emitted in the form of X-ray, called characteristic X-rays, where the inner penetrating power is proportional to 1 over lambda. Applications of X-rays. In medical science, it is used as a diagnostic tool for fractures or cracks in bones or tooth decay. BaSO4 or such dyes are used to study any defect in intestines, lungs, and nervous systems. As a therapy, it is used to treat cancer. It is used in food technology to increase the life shelf of food. It is used in engineering to find the cracks in machine parts, particularly those which are to be sent in space or used in space shuttles. It's used in detectors at airport or checkposts. In crystallography, it is used to study crystal structures. Non-destructive technique of elemental analysis. Every element has different characteristic X-ray, and the intensity depends on the concentration of that element present in the salt. It is used in research laboratories, and X-rays cause photoelectric effect and Compton. Alright, so our topic for today is current electricity. In this chapter, आपको इन चीज़ों की strong knowledge होनी चाहिए. Current is the flow of electrons. आपको conventional current की भी knowledge होनी चाहिए. Current is defined as the rate of flow of charge. करंट और चार्ज का रिलेशन है Q equals to IT. Charge is the product of current passing through a point in time t. The units of current are amperes and charge is measured in coulombs. When using an ammeter to measure current, ensure that the ammeter is connected in series to the device being studied. The conventional current in a circuit is defined as that current which passes from a point at higher potential to a point at a lower potential, as it represented a motion of positive charges. Electric current. Current is defined as the rate of flow of charge. The relation between current and charge is I equals to Q over T. Current का unit है amperes. The current will be 1 ampere when a charge flows at a rate of 1 coulombs per second. 1 ampere equals to 1 coulombs over 1 second, which is equal to 1 coulombs per second. जब आप एमीटर यूज़ कर रहे हैं करंट मेजर करने के लिए, आपको इंश्योर करना है कि एमीटर सीरीज़ में कनेक्टेड है उस डिवाइस के जो स्टडी हो रही है. Electric current in a wire. Motion of current requires an electric field inside the wire so that the electrons can experience force and move in the direction of the electric field. For a wire with zero current, the average velocity of the electrons is zero, as the directions cancel out the velocity of each individual electron. Also, as the potential difference is zero, no electric field when zero current. Drift velocity. In physics, a drift velocity is the average velocity attained by charged particles, such as electrons, in a material due to an electric field. In general, an electron in a conductor will propagate randomly at the thermal velocity, resulting in an average velocity of zero. Applying an electric field adds to this random motion a small net flow in one direction. This is the drift. The drift velocity of 10 to the power negative 3 meters per second. Ohm's law. It states that the current through a conductor is proportional to the potential difference across it, while the physical conditions such as temperature are constant. V is directly proportional to I. V equals to IR. Here you can see current and voltage graph. As the voltage increases, current also increases. The gradient is 1 over R. Ohmic conductors are those that follow Ohm's law. Hence, if a known potential is applied across an ohmic conductor and current measured using an ammeter and a graph of current against potential is drawn, the reciprocal of the graph, the gradient, would give the resistance of the conductor. Temperature must be kept constant while performing this experiment. Resistance is defined as hindrances in the motion of the charged particles such as electrons. It is the ratio of potential difference to the current flowing through a device. It's measured in ohms, and R equals to V over I. Resistance of a wire. To calculate the resistance of wires with given cross-sectional area and length, the following relation is used. Resistance R equals to rho multiplied by L over A, where rho is the resistivity of the material, L is the length of the wire, and A is the cross-sectional area of the wire. Internal resistance. Most power sources have an embedded resistance in the flow of current, known as internal resistance. It results in the reduction of the potential difference across the power source, because the internal resistance has some voltage across itself, hence resulting in decreased potential of the battery. Here you can see we've got 5 different currents. The new EMF of the cell is given by EMF equals to IR load plus IR internal. EMF equals to V load plus V load internal plus V internal. V load is also called terminal potential difference of the battery. Combination of resistances. Series resistors. Characteristics of circuit of resistance in series. Total potential difference is directly proportional to the individual resistance. Total resistance is greater than greatest individual resistance. You can see V1, V2, V3 are 1, 2, 3. Your I, which is your current, and V, which is your voltage. This is the positive side and the negative side. Req equals to R1 plus R2 plus R3. Effective resistance is always greater than the greatest resistance of the circuit. Parallel resistors. Characteristics of resistances in parallel circuit. Potential difference remains the same across each resistor. Total current equals to sum of individual current. I equals to I1 plus I2 plus I3. Individual currents inversely proportional to individual resistance. Effective resistance is always less than the least individual resistance of the circuit. The reciprocal of individual resistance is equal to the sum of the reciprocals of individual resistance. 1 over Req equals to 1 over R1 plus 1 over R2 plus 1 over R3, and so on. Potential difference. It's the conversion of energy from electrical potential energy to other forms when a unit charge passes through a circuit. It is also described as the ratio of power to current in a device. Potential difference equals to work done over charge, which is equal to power supplied over current. V equals to W over Q equals to V over I. When using a voltmeter to measure potential difference or EMF, connected in parallel to the device being studied. Resistivity. The resistance of 1 meter cube of substance called as resistivity of or specific resistance. Rho equals to R multiplied by A over L. The unit of resistivity is ohm per meter. Ohm meter. Temperature coefficient of resistance. Fractional change in resistance per degree change in temperature is called the temperature coefficient of resistance. Alpha equals to RT minus RO over R naught multiplied by T. The unit temperature coefficient of resistance is per Kelvin. Temperature coefficient of resistivity. Fractional change in resistivity per degree change in temperature is called the temperature coefficient of resistivity. Beta equals to rho T minus rho 0 over rho naught multiplied by T. The unit temperature coefficient of resistivity is per Kelvin. Electromotive force, or also known as EMF, is defined as the energy transferred from other forms to electrical energy when a unit charge moves around a circuit. EMF equals to W over Q. The difference between electromotive force and potential difference is that in potential difference, energy is converted from electrical to other forms in potential. On the other hand, in EMF, it's converted to electrical from other forms in EMF. Electric power is defined as the rate by which electrical energy is transferred in a circuit. It is also known as the rate of doing work. Mathematically, P equals to E over T, where P is the power and E is the work done. Furthermore, we know that E equals to VQ, where V is the voltage and Q is the charge. Substituting this in the equation of power, we get P equals to VQ over T. We also know that I equals to Q over T, so we get our basic formula of power given by P equals to ID. Electric power is measured in watts. Maximum power output is P equals to E square R over R minus R square plus 4RR. For maximum power output R equals to R, P max equals to E square over 4R. Kilowatt hours. Another method to measure the usage of electrical energy in commercial and residential applications is the kilowatt hour unit. This is a unit of electrical energy. It is equal to the amount of energy consumed by an appliance of 1000 watt if it was kept running for 1 hour. 1 kilowatt hour equals to 3600 kjoules. 1 kilowatt hour equals to 3.6x 10 to the power 6. 1 kilowatt hour equals to 3.6 megajoules. Kirchhoff's laws. Kirchhoff's first law states that the sum of currents entering a junction is equal to the sum of currents leaving the junction, or the algebraic sum of all the currents is 0. This law is based on the principle of conservation of charge, and it's also known as current law. Here you can see I1 plus I5 plus I4 equals to I2 plus I3. And if you add these all, the sum is 0. Summation I equals to 0. Convention. Current flowing towards the junction is positive. Current flowing away from the junction is negative. Kirchhoff's second law states that in a closed loop circuit, the sum of the potential differences is 0, or the sum of EMF is equal to the sum of potential differences across all resistances or loads. Voltage law is based on the conservation of energy. Here you can see V1 plus 2 plus 3 equals to V. Capacitance. Capacitors are components of circuits used to store charge. They are made up of two parallel conducting plates with an insulator medium between them called dielectric. When a potential is applied, electrons accumulate and are stored on the negative plate. After some time, the potential difference becomes equal to that across the battery. Hence, the capacitor is fully charged and the magnitude of positive and negative charge is equal on the plates. When potential is removed and capacitor is plugged into a circuit, it discharges exponentially with time and powers the circuit until it runs out of charge. The quantity that defines how much charge a capacitor can store is called capacitance. C equals to Q over V, where Q is the charge and V is the potential across the plates. It's measured in farads or coulombs per volts. Capacitors can store only small amounts of charge. Hence, capacitance measured in microfarads or picofarads. Parallel plate capacitors. For parallel plate capacitors, area of plates A and distance between them D can also be used to approximate the capacitance given the permittivity of the dielectric E. Capacitance C equals to EA over D. Capacitors store energy in the form of electric potential because of the work done to accumulate electrons on the negative plate and to remove them from the positive plate. Energy equals to 1 over 2 Cv square, which is equal to 1 over 2 Qv. Capacitors in series and parallels. When capacitors are connected in parallel, the total capacitance of the circuit is the algebraic sum of the individual capacitance of each capacitor. Capacitance in parallel is C equals to C1 plus C2 plus C3. When capacitors are connected in series, the total capacitance of the circuit is given by 1 over C equals to 1 over C1 plus 1 over C2 plus 1 over C3 and so on. Wheatstone bridge. For measuring accurately any electrical resistance, Wheatstone bridge is widely used. There are two known resistors, one variable resistor and one unknown resistor, connected in bridge form as shown below. By adjusting the variable resistor, the current through the galvanometer is made zero. When the current through the galvanometer becomes zero, the ratio of two known resistors is exactly equal to the ratio of adjusted value of variable resistance. Alright, so our topic for today is physics of solids. So the classification of solids are in the following types: crystalline, amorphous or glassy, and volumeric. In crystalline solids, there is a regular arrangement of molecules. The neighbors of every molecule are arranged in a regular pattern that is constant throughout the crystal. There is thus an ordered structure in crystalline solids. In amorphous solids, there is no regular arrangement of molecules like that in crystalline solids. Amorphous solids are more like frozen liquids with a disordered structure. Amorphous solids are also called glassy solids. Volumeric solids may be said to have more or less solid materials with structure that is intermediate between order and disorder. They can be classified as partially or poorly crystalline solids. Plastics and synthetic rubbers are termed polymers because they are formed by polymerization reaction. These materials have rather low specific gravity compared with even the lightest of metals and yet exhibit good strength to weight ratio. Polythene, polystyrene, and nylon, etc. are examples of polymers. Applying force on a spring. If a force is applied on a body resulting in its deformation, when the force is removed, the body can either return to its original shape, मतलब कि elastic deformation, जिससे कि rubber spring होती है, or it can deform permanently, hence not returning to its original shape, called inelastic deformation, जैसे कि clay की होती है. Hooke's law states that the force required to stretch or compress a spring is proportional to displacement x by which it is stretched or compressed, provided that the elastic limit is not crossed. Tension in spring, F equals to negative kx, where x is the extension and k is the proportionality constant denoting stiffness. Stress and strain. Stress is the force applied per unit area. It is measured in pascals or newtons per meter square. Stress is equal to force over area. Strain is the extension of the material per unit length. It has no units since it is a ratio of two lengths. Strain equals to extension over original length. Elastic constant. The ratio of stress to strain is a constant for a given material, provided the external applied force is not too great. This is called modulus of elasticity and can be mathematically described as modulus of elasticity equals to stress over strain. The units of modulus of elasticity are newtons, nm2 or pascals. In case of linear deformation, the ratio of tensile or compressive stress to tensile or compressive strain is called Young's modulus. Y equals to F over A over delta I over L. For three-dimensional deformation, three-dimensional deformation, when volume is involved, then the ratio of applied stress to volumetric strain is called bulk modulus. K equals to F over A over delta V over V, where dV is the change in original volume V. However, when the shear stress and the shear strain are involved, then the ratio is called shear modulus. G equals to F over A over tan theta. Stress strain graphs. So this is your proportional limit, this is your elastic limit, या फिर yield point, elastic behavior, plastic behavior. This is your fracture point. This is your stress strain graph. The graph shows the different stages in the extension of a material under stress. Point A shows the limit of proportionality, or the point until which force is proportional to the extension. F is proportional to x. From origin of the graph to point A, the Hooke's law is obeyed and the graph is a straight line, and the gradient of the graph gives Young's modulus. Point B, the elastic limit, is the point until which the wire stretches elastically. Hence, a wire can regain its original shape only if the force is removed before the elastic limit is crossed. Work done in stretching the wire can be regained completely until this point. Beyond point B is the region of plastic deformation, where the wire extends non-elastically, hence not regaining to its original shape when the force is removed. The work done to stretch the wire cannot be recovered in this area. Point D shows the breaking or fracture point at which the object breaks. The gradient of a force F against area A graph gives the stress on the material, and the area under the graph gives the work done or energy stored. Also note that the breaking force, or the maximum load the wire can hold, is proportional to the cross-sectional area of the wire. Breaking force is directly proportional to the cross-sectional area. Material properties. The graph shows the variation of stress with strain for 4 different materials. Material A is the most strong and stiff because of a higher slope, showing high Young's modulus. Examples include strong metals and steel. Material B is the most brittle because it breaks before showing any elastic behavior. Glass is a good example of brittle materials. Material C is the most ductile because it extends the most before breaking. Ductile materials undergo plastic deformation before breaking. Example, copper wire. Material D needs lower stress to break than C, hence is less ductile than C. Here you can see loading and unloading, the stress and strain graph for rubber, and this is stress and strain graph for polyethylene, and you can see the loading and unloading. The graphs above show the variation of stress and strain for rubber and polyethylene when these materials are loaded and unloaded. मतलब ये force apply होती है और जब move होती है. For rubber, after loading and then unloading, the rubber would regain its original shape, but some energy is lost, shown by the area under the graph. The strain energy is lost in the form of heat and can be found by finding the area between the two curves. Example, energy lost equals to area under loading curve minus area under unloading curve. For polymers such as polyethylene, the material does not regain its original shape or is permanently deformed after the unloading of the force. Hence, it undergoes plastic deformation. Energy is lost in this case too, as shown by the graph. Energy in force extension graphs. When the wire is stretched, work is done on the wire which is stored in it in the form of elastic potential energy. This work can be regained if the wire doesn't cross its elastic limit. If the wire crosses its elastic limit, some of the elastic potential energy stored in the stretched wire is lost as heat. Work done in stretching a wire by an amount delta x is given by work, and here you go, FDX. Hence, work done can be found by simply finding the area under a force extension graph. Assuming that the elastic limit is not crossed, the graph is a straight line with a constant gradient. Hence, the area under the graph is denoted by a right angle triangle as shown. Force F, extension x, work done equals to area under the graph. Elastic potential energy equals to work done equals to 1 over 2 Fx. Valence band, conduction band, and energy gap. The electrons of an element can reside in valence band or conduction band. The electrons in the conduction band have greater mobility and are responsible for the flow of current in conductors. The electrons residing in valence band must be provided with energy so that they can jump to the conduction and start to move, causing a flow of current. The amount of energy required depends on the band gap between conduction band and valence band and is known as generally the energy band gap. The insulators have a high energy band gap, meaning they require a lot of energy for their electrons to jump to the conduction band and conduct electricity. Materials known as semiconductors have low energy band gap values and they can be made to conduct electricity with the help of doping. N-type semiconductor. Silicon is a semiconductor, and when it is doped with N-type impurity like arsenic, phosphorus, which have 5 valence electrons, an N-type semiconductor is created. The 4 valence electron bonds with the 4 out of 5 valence electron of phosphorus. The fifth free electron is responsible for the flow of current. This is an M-type semiconductor. P-type semiconductor. When silicon is doped with trivalent impurity like boron, the 3 electrons bond with 3 neighboring Si atoms, whereas the 1 electron missing the covalent bond of the fourth silicon atoms is called a hole, which is a vacant space for an electron to take. This is your p-type semiconductor. Here you can see there's a free electron here, whereas here there's a hole in the p-type semiconductor. Paramagnetic, diamagnetic, and ferromagnetic substances. Paramagnetic substances are the substances which are weakly attracted to magnetic fields. Their orbitals are partially filled and have unpaired electrons, and magnetism in these materials is caused by spin and orbital motion of electrons. Oxygen is a paramagnetic material. Diamagnetic materials are the materials which are repelled by magnetic. They have completely filled orbitals. The magnetic fields caused by individual electrons in these materials cancel each other out. Copper is an example of diamagnetic material. Ferromagnetic materials. These materials are paramagnetic in nature, but their magnetic nature is much more intense. These materials are strongly attracted by a magnet. Alright, so our topic for today is heat and thermodynamics. इस चैप्टर में you should have a sound knowledge of kinetic theory of gases and the ideal gas equation. कुछ important features kinetic theory of gases के हैं. A finite volume of a gas consists of a very large number of molecules. At standard temperature and pressure, there are approximately 3 times 1025 molecules in 1 cubic meter of a gas. The molecules are merely point masses. The distance between them is very large as compared to their dimensions. The molecules are continuously in motion. They have velocities in all directions, ranging from minimum to maximum. The velocity of the molecules increases with temperature. In steady state, the molecules are continuously colliding against each other and with the walls of the container. The molecules are perfect elastic spheres and exert negligible force of attraction on one another or on the walls of the container. When the collision occurs between the molecules, there is no loss of momentum or the kinetic energy. Collision is always elastic basically. There is no loss of momentum or kinetic energy. Laws of mechanics are assumed applicable to the motion of the molecules. हम शुरू करते हैं gas laws. So basically charge law or law of volumes relates volume changes of gases to changes in temperature. It states that if pressure of a sample of gas is kept constant, the volume is directly proportional to temperature. So V is directly proportional to temperature. V over T equals to K. The following important equation is hence obtained and can be applied when making comparisons of two different conditions under the sample of the same gas. V1 over T1 equals to V2 over T2. This relation is only true for constant pressure. Paul's law states that when temperature and amount of gas is kept constant in the system, the pressure exerted by the ideal gas is inversely proportional and inversely related to its volume. P is proportional to 1 over V, and PV equals to K. P1 V1 equals to P2 V2. Ideal gas equation. The ideal gas law is derived from the kinetic theory as it defines the motion of gas particles or molecules at a microscopic level. It illustrates the relations between certain quantities associated with gases. These quantities include volume, temperature, pressure, and number of moles. For an ideal gas, PV equals to nRT, where N is your number of moles and R is the universal gas constant. here PV equals to NKT, where N, capital N, is your number of molecules and K is the Boltzmann constant. Comparison of the behavior of ideal gases and some common real gases. These changes in pressure is as follows. Here you can see your pressure in ATM compared to carbon dioxide, hydrogen, nitrogen. Here's your gas pressure. So the equation for the pressure of ideal gases can be derived using the kinetic theory of gases, and it's given by P equals to 1/3 rho C2, where rho is the density of the gas. Internal energy of ideal gases. Ideal gases are considered to have negligible intermolecular forces between its molecules, hence zero potential energy. So the internal energy of ideal gases is equal to the sum of the kinetic energy of the molecules. Hence the internal energy of an ideal gas is given by internal energy U equals to number of molecules N multiplied by your average kinetic energy of molecules. Average kinetic energy equals to 1/2 mc2, or and is also equal to 3/2 kT. Internal energy U equals to 3/2 nkt. This formula applies to monoatomic gases, while for diatomic gases the formula becomes internal energy U equals to 5/2 nkt, where c square is the mean square velocity, n is the number of molecules, k is the Boltzmann constant, and T is the absolute temperature. The root mean square velocity or the gas particles is given by root mean square equals to under root c square and is equal to v1 square plus under root v1 square plus v2 square plus v3 square plus dash dash plus v square n over n, where v1 square plus v2 square plus v3 square plus dash dash plus v square n are the squares of velocities of the gas particles in constant random motion, and n is the number of particles. Ideal gases obey both Joule's and Boyle's law. Real gases can be made to behave almost ideally at low pressures and high temperatures. For an ideal gas at a constant temperature, PV is constant, as suggested by the ideal gas equation. Laws of thermodynamics. So the first law of thermodynamics states that energy is conserved. Its form can be converted. The second law states that energies can flow and equilibrate. Third law states that driving force for equilibration is uniquely defined. And zeroth law, thermal equilibrium, is transitive. Zeroth law of thermodynamics. The zeroth law of thermodynamics states that if two systems A and C are in thermal equilibrium with another system B, then the two systems A and C are in thermal equilibrium with each other. This law defines the use of thermometer as an instrument used to compare the temperature of two bodies in equilibrium, matlab ki having the same temperature. Thermometer in our case is system B. First law of thermodynamics. The first law of thermodynamics states that the increase in internal energy of a system is equal to the sum of the heat supplied to the system and the work done on the system. So, change in internal energy equals to work done on the system plus Q, which is the heat energy. Here, delta U is the increase in the internal energy of the system, W is the work done on the system, and Q is the heat energy supplied to the system. Sign conventions must be kept in mind when performing calculations related to the change in internal energy. Second law of thermodynamics. Here you can see energy before and energy after, they're equal. It's a visual diagram. Second law of thermodynamics. The second law of thermodynamics states that the entropy of an isolated system does not decrease. This is the reason why heat doesn't flow from a cold body to a hotter body. For a non-isolated body, the entropy may, however, decrease, but the total entropy of the universe will always increase whatsoever. For an irreversible process, the entropy of the system and the environment increases. It's greater than zero basically. Change in entropy is greater than zero. Change in entropy for a reversible process. Delta S equals to delta Q over T, where delta S is greater than or equal to 0. where delta Q is the change in energy and T is the thermodynamic temperature of the closed system. Here you can see this. TH, which is your heat source, QH, heat engine, W equals to QH minus QL, here QL, and then there's TL, which is heat sink. Entropy. For learning the second law of thermodynamics, we must understand the concept of entropy. Entropy is the measure of disorderliness or randomness of particles in a system. It relates to the number of configurations of different arrangements of particles in a system. Highly ordered. Increase in entropy, more disordered. Third law of thermodynamics. The third law of thermodynamics states that the entropy of a system approaches a constant as the absolute temperature of the system reaches zero. This is because at temperatures close to 0 kelvins, there are less possible states for particles or atoms. At 0 kelvins, there is only one microstate of particles. The relation between entropy and number of microstates is as follows. S equals to K ln delta, where S is the entropy, delta is the number of microstates or number of possible arrangements of particles, and K is the Boltzmann constant. At 0 Kelvin, delta equals to 1. Hence, ln1 equals to 0. So, S equals to 0. Work done on gases. The first law of thermodynamics states that the increase in internal energy of a system is equal to the sum of the heat supplied to the system and the work done on the system. Here, delta U equals to delta W plus delta Q, where delta U is the increase in the internal energy of the system, W is the work done on the system, and Q is the heat energy supplied to the system. Work done on gases and thermodynamics. So basically, the work done for a gas with constant pressure is given by work done equals to W equals to P delta V, where P is the pressure of the gas and delta V is the change in volume of the gas. Hence, delta U equals to P multiplied by delta V plus delta Q. Constant pressure process. For an isobaric process whereby a gas is expanded while keeping the pressure constant, the following graph is observed. The work done for a gas with constant pressure is given by work done W equals to P delta V, where P is the pressure of the gas and delta V is the change in volume of the gas. Hence, delta U equals to P delta V plus Q. It's important to note that the area under pressure against volume graph would give us the work done. Constant volume process, isospheric. For an isovolumetric process whereby pressure is increased while keeping the volume constant, the following graph is observed. Here, Pi and Pf, this is your P and this is your V. Here's your V, and this is I and F. A constant volume process appears on a PV diagram as a vertical line. The work done for the gas at constant volume will be 0 as delta V equals to 0. W equals to P delta V equals to P0, which is 0. According to first law of thermodynamics, delta U equals to P delta V plus Q. Delta U equals to 0 plus Q. Delta U equals to Q. Constant temperature process, isothermal. In the case of an ideal gas, the internal energy depends upon only temperature. So at constant pressure, the change in internal energy will be 0. Q equals to W plus delta U. Delta U equals to 0. Q equals to W. Hence, energy supplied to the system is equal to the work done by the system. Q equals to negative delta W. Adiabatic process. The process in which no heat enters or leaves the system is called as adiabatic process. Q equals to 0. Even though no heat energy is lost or gained by the system in an adiabatic system, there is always a temperature change. This change in temperature is due to change in pressure of the gas without addition or removal of any heat energy. If the pressure of a system is increased by more than just the work done by the surroundings, using a piston for instance, assuming that no heat energy change occurs, the gas is said to undergo adiabatic heating. According to the first law of thermodynamics, Q equals to W plus delta U. 0 equals to W plus delta U. W equals to negative delta U. Work done on gases, adiabatic. If a system does work on the surroundings, reducing its pressure without any change in heat, The system is said to achieve adiabatic cooling. For higher temperatures, the graphs would shift upwards. If a graph of volume against pressure for a complete cycle of processes is given, we can infer that the change in internal energy, delta U, equals to 0 after each cycle. Also, the total work done is equal to the area bounded by the circle as shown on the graph below. Area equals to work done. This is a pressure volume graph. Temperature. Temperature can be defined as the degree of hotness which determines the direction of flow of heat from one body to another when they are brought in thermal contact with each other. Temperature scales. To measure the temperature quantitatively, temperature scale is needed. The temperature scale depends on two fixed points whose values are always same under similar conditions. There are three different temperature scales generally used today: Fahrenheit, melting point of ice equals to 320 Fahrenheit, boiling point of water equals to 2120 Fahrenheit. Scale is divided in 180 degrees between melting point of ice and boiling point of water. Melting point of ice equals to 0 degrees Celsius centigrade. Boiling point of water equals to 1000 Celsius. Scales is divided in 100 degrees between melting point of ice and boiling point of water. Melting point of ice in Kelvin is equal to 273. Boiling point of water equals to 373. Scale is divided in 100 points between melting point of ice and boiling point of water. Molar specific heat. The molar specific heat of the substance is defined as the heat required to increase the temperature of one mole of the substance through 1 Kelvin. Molar specific heat at constant volume. The molar specific heat at constant volume is the amount of heat required to raise the temperature of 1 mole of the gas through 1 Kelvin at constant volume, and is symbolized by CV. Delta U equals to QV equals to CV delta T. Molar specific heat at constant pressure. The molar specific heat at constant pressure is the amount of heat required to raise the temperature of 1 mole of the gas through 1 Kelvin at constant pressure, and it is symbolized by Cp. Qp equals to Cp delta T. Relation between Cp and Cv. Cp minus Cv equals to R. Molar specific at constant pressure is always greater than molar specific heat at constant volume. Alright, so our topic for today is electrostatics. तो दो किस्म के चार्ज होते हैं, पॉजिटिव और नेगेटिव. पॉजिटिव में नंबर ऑफ इलेक्ट्रॉन्स नंबर ऑफ प्रोटॉन से कम होते हैं. नेगेटिव चार्जेस में नंबर ऑफ इलेक्ट्रॉन्स नंबर ऑफ प्रोटॉन से ज़्यादा होते हैं. किसी भी न्यूट्रल मटेरियल में नंबर ऑफ पॉजिटिव और नेगेटिव चार्जेस हमेशा इक्वल होता है. अगर कोई इम्बैलेंस है तो मटेरियल उसके मुताबिक चार्ज हो जाता है. ये आप देख सकते हैं, दिस इज योर न्यूक्लियस. ये आपका प्रोटॉन है which is positive, neutron which is neutral, and electron which is negative. Coulomb's law and its applications. Coulomb's law states that the electrostatic force acting on each charged particle is directly proportional to the product of the magnitude of charges and inversely proportional to the square of the distance between them. This is your charge Q1 and Q2, F12 and 21 are distance, I guess. F21 equals to negative F12 equals to K multiplied by Q1 Q2 over R2, where Q1 and Q2 are the magnitude of the charges. K is the Coulomb's constant with value 9 times 10 to the power 9 Newton meter square per Coulomb, and R is the distance between the centers of the charges. Electric field patterns point charges के लिए. So ये electric field patterns हैं दो individual point charges के लिए. ये positive है. You can see field lines going away from the positive charge, and you can see them going towards the negative charge. For 2 point charges close to each other, the field patterns are according to the law of electrostatics. F21 और F12 ये देखिए आप पॉजिटिव से नेगेटिव तक जाता है, और इसमें पॉजिटिव लाइट चार्जेस हैं तो रिपेल करते हैं. The field lines are away from each other. Particle placed at point P as shown in the above image would experience zero electric force. ये भी नोट करें that the force acting on both charged particles in each case is equal in magnitude and opposite in direction, hence satisfying Newton's third law. F21 equals to negative F12. Electric field patterns for plates. Following images show electric field patterns for two individual point charges. For two charged parallel plates, The direction of electric field is from positively charged plate to the negatively charged plate. The strength of the electric field in this case can also be found using E equals to V over D, where V is the potential difference between the plates and D is the distance between the plates. V is the distance between the plates, V is your voltage, and E is basically this is your direction from positive to negative, usually with equal gaps between field lines. The electric field produced due to two charged parallel plates is uniform, मतलब एक direction में with equal distance. Similar diagrams can be drawn for other arrangements such as a charged particle and a charged plate, two non-parallel charged plates, etc. Electric fields. The regions where charged particles experience force. The direction of an electric field is defined by the direction of the electric force acting on a charged particle placed in the electric field. एक negative charge के लिए the direction of the electric field is opposite to the direction of force. लेकिन positive charge के लिए electric field is in the direction of the force acting on the charged particle placed in the electric field. Hence, electric field lines represent the direction of force that would act on a positive charge when it is placed in the field. Electric field strength. इसका यूनिट होता है न्यूटन्स पर कूलम, is defined as the force exerted on a charged particle per unit positive charge. इसका फॉर्मूला होता है E equals to F over Q, जहाँ पे F is the force acting on the charged particle और Q is the amount of charge. ये एक वेक्टर क्वांटिटी है. Electric potential. Electric potential due to a point charge is the work done in moving a unit positive charge from infinity to a point in the electric field. Electric potential V equals to W over Q. It's measured in volts. V from the formula of E involving Q and R, we can see that V would also be written as V equals to E multiplied by R. V equals to kg over R. K cube over R. Electric potential energy. U of a point charge is defined as the work done by the electric field force to move the charge across a potential difference of V. Electric potential energy U equals to QV, U equals to K multiplied by Q1 Q2 over R. Hence, electric potential energy is inversely proportional to distance, and for unlike charges, the maximum value of electric potential energy can be 0 at infinity as shown. For unlike charges, the product of Q1 and Q2 is negative, hence the negative sign. For like charges, the product is positive, hence the potential energy is positive. Gauss's law and its applications. This law states that the net flux of an electric field through a closed surface is directly proportional to the charge enclosed in it. Mathematically, it's given by Gauss's law, which is your electric flux equals to Q, which is your enclosed charge C, over permittivity of free space. इसकी value होती है 8.85 multiplied by 10 to the power negative 12. Electric field due to an infinite plane of sheet. Consider an infinite large sheet with a charge density of rho C over m square. According to Gauss's law, the total electric flux through a surface is proportional to the charge enclosed by the surface. Mathematically, it is given by electric flux equals to Q over epsilon, your permittivity of free space, where electric flux is where this is the flux, Q is the charge enclosed, and E naught is the permittivity of free space. So drawing a Gaussian surface around this plane of sheet as shown in the diagram below, we get this is your area A, this is your positive charges and your direction of the lines. Charge Q equals to this multiplied by A, delta A. We know that flux is Q over epsilon naught, and 2 E dot A, where E is the electric field and A is the cross-sectional area. Equating these two equations for flux, we get delta A over epsilon naught over your permittivity of free space equals to 2 E dot A. E equals to delta over 2 E naught, permittivity of free space. Electric field between two oppositely charged parallel plates. By using Gauss's law, we can find that the electric field between the oppositely charged plates is E equals to delta over permittivity of free space. Electric potential. The amount of work required to bring a unit positive charge from infinity to that point against the electric field of a given charge without changing kinetic energy. V equals to 1 over 4 pi multiplied by permittivity of free space, and this whole multiplied by Q over R. It's a scalar quantity and its unit is volt. 1 volt equals to 1 J over 1 C. The dimensions are M1 L2 D 3A1. Potential difference. Work done, a unit positive charge from one point to another called as potential difference. Delta V equals to W over Q naught. The unit of potential difference is also volt, electron volt. The amount of energy equal to 1.6 multiplied by 10 to the power negative 19 joules is called electron volt and it's denoted by 1 eV. It's defined as the amount of energy acquired or lost by an electron as it traverses a potential difference of 1 volt. 1 eV equals to 1.6 times 10 to the power negative 19 joules. Capacitors are devices used to store charge and it's measured in capacitance. The charge storing capability of the capacitor depends on the voltage applied and the physical properties of the materials. Mathematically इसका formula है C equals to Q over V. इसका SI unit farad होता है. The capacitance of capacitor will be 1 farad if when a 1 coulomb's charge is stored on the plates of capacitor and then potential difference between them is 1 volt. 1 farad equals to 1 coulomb over 1 volt. 1 farad equals to 1 coulombs per volt. For a parallel plate, capacitance is given by CVAC equals to A, permittivity of free space, over D, where A is the cross-sectional area of the plates and D is the distance between the plates. The energy stored in the capacitor is in the form of electric fields and it's given by E equals to 1 over 2 CV square, whereas जहाँ पे C capacitance है और V voltage है. The charge stored on the capacitor depends on the voltage applied and the capacitance of the material. Q equals to CV. This buildup of charge is never instantaneous and takes up some time and it's dependent on the series resistance in the circuit and the capacitance. Important functions of capacitor: timer, time setting in almost all automatic devices; time-based circuit in CRO, sawtooth generator; filter circuits, low pass, high pass and band pass; oscillators, LC oscillators, F naught equals to 1 over 2 pi under root LC. This is your tuner circuit in radio. It's a trimmer in frequency setting with quartz oscillator, integrating and differentiating circuits, voltage multipliers, clamping circuits, phase shift producer in one RC section, in AC motor to enhance torque, converts active power to passive or Wattles power. Dielectrics. Insulator placed between the fields of a capacitor is called dielectric. Dielectrics get polarized with opposite polarity to electric field. The capacitance of parallel plate capacitor increase in the presence of dielectric. Cmed equals to A multiplied by epsilon naught multiplied by ER over D. Cmed over Cvac equals to ER. An increase in the capacitance of capacitor in the presence of dielectric is due to electric polarization of dielectric. Polarization is a phenomenon of appearance of opposite charges on the surface of a plate subject to the electric field. Polarization charges are called induced charges. Charging and discharging of capacitor. The figure A shows resistor capacitor RC circuit. When a switch S is connected with terminal 1, the combination is connected with battery which starts charging with capacitor. The capacitor is not charged immediately, rather charge is built up gradually to equilibrium value. The figure B shows resistor capacitor RC circuit. When a switch S is connected with terminal 2, the combination is connected with battery which starts discharging the capacitor. The capacitor is not charged immediately. A and B में आप फर्क दे सकते हैं. Here it's 1 to S, but here it's 2 to S. Terminal 1 है यहाँ पे terminal 2 है. यहाँ पे A में charge होता है capacitor और B में I guess discharge होता है. Time constant for RC series circuit RC equals to T. This product is known as time constant. How fast the capacitor is charging or discharging depends on time constant. For large RC value, the capacitor will take more time to completely charge. Alright, so our topic for today is electromagnetic induction. When a fluctuating magnetic field is brought near a closed circuit, electric current is induced in the closed circuit. Two important laws govern the magnitude and the direction of the induced EMF. Faraday's law और Lenz's law को मिला के Newton's equation बनता है. Motional EMF. The EMF induced by the motion of a conductor across a magnetic field is called motional EMF. Magnitude of motional EMF in a rod of length L moving with velocity v across a magnetic field of strength B, making angle Q. It is epsilon equals to VBL sin Q. Two important laws govern the magnitude and the direction of the induced EMF: Faraday's law of induced EMF and Lenz's law, and understand the link between them. Faraday's law. It states that the magnitude of the induced EMF is proportional to the rate of change of magnetic flux linkage. Magnetic flux linkage is the product of N, the number of turns of the coil, and the magnetic flux, phi. Induced EMF equals to negative N multiplied by change in phi over change in time. So, the magnitude of the induced EMF is dependent on three quantities: magnetic field density B, speed of motion of magnet, and number of turns of coil N. Lenz's law. Lenz's law states that the direction of the induced EMF is such that it always opposes the change producing it. Here you can see this is the south pole of the magnet and the north pole. It's pointing that way, and the coils are moving upwards. And here it's the opposite, as the poles have been reversed. This law can be proved from the fact that when the north pole of a magnet is moved towards the coil, current is induced in the coil such that a north pole is induced on the face of the coil, being opposed by the north pole of the magnet. This causes repulsion to movement of the magnet or a resistance in its motion. Similarly, when the north pole is moved away from the coil, the direction of the current and hence the polarity of the induced pole changes to the south pole, hence causing attraction, hence a resistance to the motion of the magnet. Also note that the polarity of the induced pole on the coil is determined using the right hand grip. Lenz's law and law of conservation of energy. The induced EMF produces a current that opposes the change in flux, and hence the energy as the chain starts induction opposes and slows the change. If the induced EMF were in the same direction as the change in flux, then that would give us free energy for no apparent source, violating conservation of energy. Thus, Lenz's law is in accordance with the law of conservation of energy. Here's a direct example. A straight wire carrying current I lies on the ground. A circular loop of wire is pushed across the ground from position 1 to position 2, as shown in the diagram. Note that the diagram is the top view of the ground and the loop of wire. Determine the direction of the induced current in the loop at position 1 and also at position 2. According to the right hand rule, on straight carrying current wire, the following magnetic field pattern is observed. At position 1, the circular loop experiences a magnetic field directed out of the page. So according to Lenz's law, the EMF induced in the coil would be such that it would oppose the magnetic field of the wire at position 1. As the magnetic field due to wire is outwards, EMF would be induced such that the magnetic field due to the coil would be directed inwards. Using right hand rule, pointing the thumb into the page feels the direction of induced current to be clockwise. At position 2, the loop experiences a magnetic field directed into the page due to the current carrying wire. So current induced would be such that the magnetic field due to coil would be out of the page. So current induced would be anti-clockwise. Practice question. A rectangular loop of wire has 200 turns, each having an area of 4 times 10 to the power negative 3 meters square. A magnetic field directed at 30 degrees to the normal of the loop is turned on at t equals to 0. Magnetic field increases linearly to 0.5 t in t equals to 0.5 s. What is the magnitude of the average induced EMF in the loop, given that the loop is a closed circuit having a resistance of 5 omega? Find the induced current. Solution: epsilon equals to negative n multiplied by change in change in time, where phi equals to AB cos theta. We know that area A and angle theta are constants, so we can pull them out of the derivative. Epsilon equals to negative NA cos theta multiplied by change in B multiplied by change in T. Given the fact that B increases linearly to 0.5 t in 0.5 seconds, we note that B over T equals to 0.5 over 0.5, which is equal to 1. Epsilon equals to NA cos theta, which is equal to 200 times 4.0 times 10 to the power negative 3 multiplied by cos 30, which is equal to 0.693 volts induced current. I equals to epsilon over R, which is equal to 0.693 over 5, which is equal to 0.139 amperes. Combining both Faraday's and Lenz's law, induced EMF E equals to negative N multiplied by d phi over dt. The negative sign shows the opposite nature of the induced nature from Lenz's law. Mutual inductance. It can be defined as the ratio of the EMF induced in the secondary coil to the rate of change of current in the primary coil. It is denoted by M. The SI unit for mutual conductance is M. Inductance is M is VSA negative 1, which is called Henry H after Joseph Henry. The mutual inductance of two coils is 1 Henry if the current changing at the rate of 1 ampere per second in the primary causes an induced EMF of 1 volt in the secondary. Self-induction. The phenomenon in which an electric circuit opposes any change of current in itself is known as self-induction. It is denoted by L. It can be derived that epsilon L equals to negative L multiplied by change in I over change in t. This equation shows that the self-induced EMF must oppose the change that produced it. That is why the self-induced EMF is sometimes called as back EMF. If the current is increased, the induced EMF will be opposite to that of the battery. And if the current is decreased, the induced EMF will aid rather than oppose the battery. Because of their self-inductance, coils of wire are known as inductors. Inductors behave like resistors. Energy stored in an inductor. Energy can be stored in the magnetic field of an inductor. The energy stored in an inductor is given as Un equals to Li2. In an inductor, energy is stored in the magnetic field. If L is the length of solenoid, then the self-inductance of the solenoid is L equals to MON2A. Generators. An electric generator uses mechanical energy to generate electricity. As the heart of both motors and generators is a wire coil in a magnetic field. In fact, the same device can be used as a motor or a generator. When the device is used as a motor, current is passed through the coil. The interaction of the magnetic field with the current causes the coil to spin. To use the device as a generator, the coil can be spun, inducing a current in the coil. An AC generator, alternating current generator, utilizes Faraday's law of induction, spinning a coil at a constant rate in the magnetic field to induce an oscillating EMF. The coil area and the magnetic field are kept constant. So by Faraday's law, the induced EMF is given by this formula. A coil turning in a magnetic field can also be used to generate DC power. A DC generator uses the same kind of split ring commutator used in a DC motor. Unlike the AC generator, the polarity of the voltage generated by a DC generator is always. Transformers. Here you can see P is your magnetic field, the direction of it. Phi is your magnetic flux. E is your epsilon is your relative permittivity, and N is your number of turns. Transformers. They are devices that transfer energy between multiple coils or circuits using electromagnetic induction. We will study induction of current in two coils only, but this concept can be extended to multiple coils. Transformer is made up of two coils of wires wound round a soft iron core. An EMF is applied to the primary coil, and due to change in magnetic flux linkage, an EMF is induced in the secondary coil. The magnitude of the EMF induced is dependent on the number of turns of the coils and the magnitude of the EMF applied to the primary coil. The result of this induction is that the EMF is either stepped up or stepped down, depending on the number of turns of coils. Step up and step down transformers. The relation between the number of turns of coil and the EMF is given by EP over ES equals to NP over NS. For a step-up transformer, EMF in secondary coil is greater, hence more number of turns of secondary coil. ES is greater than EP, hence NS is greater than NP. Conversely, for a step-down transformer, EMF in secondary coil is less, hence lesser number of turns of secondary coil. ES is less than SP, and therefore NS is less than NP. A changing magnetic field causes the electromagnetic induction, and alternating current must be applied in order for the changing magnetic field to be produced. Ideal transformer. For an ideal transformer, the power input must be equal to the power output for 100% efficiency. P in equals to P out. Therefore, EPIP equals to ESIS multiplied by ES over EP, which is equal to IP over IS. Therefore, NS over NV equals to IP over IS. Efficiency of a transformer is given by P out over P in multiplied by 100. Sources of power loss. Typical transformers have high efficiency but not 100%. Following are the sources of power loss in a transformer. Eddy currents leading to heating of the coil, hence loss of energy in form of heat. To reduce heat loss due to eddy currents, laminate the core using multiple sheets of soft iron. Hysteresis, or the resistance of the core to the fluctuating magnetic field, also called hysteresis loss. To reduce heat loss due to hysteresis, use material that offers less hysteresis to make the core. The heating of the wire due to the resistance in the motion of the current. Use material of higher cross-sectional area to reduce the resistance, because resistance is inversely proportional to cross-sectional area and directly proportional to length. Some other key topics that can be asked include DC motors, back EMF effect, and DC generators. Generator. An electric generator uses mechanical energy to generate electricity. At the heart of both motors and generators is a wire coil in a magnetic field. In fact, the same device can be used as a motor or a generator. When the device is used as a motor, the current is passed through the coil. The interaction of the magnetic field with the current causes the coil to spin. To use the device as a generator, the coil can be spun, inducing a current in the coil. An alternating current generator utilizes Faraday's law of induction, spinning a coil at a constant rate in a magnetic field to induce an oscillating EMF. The coil area and the magnetic field are kept constant. So by Faraday's law, the induced EMF is given by epsilon equals to n omega A B sin theta. At theta equals to 90, epsilon naught equals to n omega A B. Therefore, epsilon equals to epsilon naught multiplied by sine omega t. I equals to I naught sine omega t. You can refer to this graph as well. A coil turning in a magnetic field can also be used to generate DC power. A DC generator uses the same kind of split ring commutator used in a DC motor. Unlike the AC generator, the polarity of the voltage generated by a DC generator is always